Hello everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look at the processes of nuclear fission and nuclear fusion. So we've kind of put these two together in a bit of a bumper lesson to end our term. To start us off though, we've got 3 questions based around our previous lesson, so have a go at answering those in your books for me. I'm going to give you about 3 minutes to do this. Let's check those answers then. So for question 1, you could have any 3 of the following: food and drink, ground and buildings, cosmic rays, radon gas, medical uses, nuclear weapons tests, or nuclear power. So any 3 of those, 1 mark for each you got right. For question 2, we've got 4 marks available. The first one is for saying it's a gamma knife. The second one is for saying that we position it to focus on the tumour. Third is for saying it moves. And the fourth is for saying that the healthy cells receive a low dose. And I just realised there's 5 marks there instead, not 4. And that means the cancer cells are killed. So a gamma knife is positioned to focus on the tumour, but it moves so the healthy cells receive a low dose, but the cancer cells get the high dose, so are killed. So that's a maximum of 5 for question 2. And then finally for question 3, 2 other uses. We could have medical tracers for 1 and sterilising equipment for the second. 1 mark for each of those, which I do believe gives us a total out of 10 today. Now, something we've already looked at in one of our earlier physics lessons is about what happens with unstable nuclei. So see if you can finish off the sentence and those bullet points in your books for me first of all. hopefully we remembered that unstable nuclei emit radiation. And the nucleus will emit one of 4 types of radiation: the alpha particles, beta particles, gamma radiation, or neutrons. So make sure you've got those right. Obviously, anything you didn't, fill in the blanks and write the corrections in. So we're going to start off by looking at the process of nuclear fission. Now you've got to be careful because the 2 processes we're going to look at today are both starting with the word nuclear, and then they both start as F's. So we've got to be really careful. Nuclear fission is the first one. Now in nuclear fission, what we're seeing is a large nucleus splitting into smaller nuclei and neutrons. Now, this isn't a process that occurs spontaneously that frequently, but if the nucleus absorbs a neutron, then fission becomes more likely. And the easy way to think of this is splitting. So we've got the S's in the middle there, 2 S's, and we're splitting that large nucleus into smaller nuclei and some neutrons. So make sure you've got those 3 sentences written in your books. Sometimes it's far easier to visualize this with a picture. So at the bottom of your screen, you can see we've got our large nucleus, first of all, and we can see that little purple blob zooming towards it from the left-hand side there. That's a neutron. So as that neutron joins with the nucleus, what happens is it's going to split to produce 2 smaller nuclei, which we can see just to the right of the arrow there, and it's also going to release 2 or 3 neutrons. The purple blob's just zipping off to the right of the screen. So this is the process of nuclear fission. We've got a large nucleus, and then as that neutron has come in, it's triggered this reaction where it's going to split into 2 smaller nuclei and 2 or 3 neutrons. And I've given you the example there of 2 fissionable substances. Now if something is fissionable, that means it's going to split easily. So we've got uranium-235 and uranium-239. So I suggest you get those 2 sentences written down, and if you want to do a little sketch of the diagram at the bottom, by all means feel free. Now, in terms of why we really care about this process of nuclear fission, it's not just one of those things we teach you about in science that's actually going to have no impact on your life whatsoever. This is actually the process that we use in nuclear power stations. Because in nuclear power stations, we've got our fissionable substance, and we're going to use this nuclear fission reaction to actually heat the water in the power plant. When we heat the water up, it produces steam. The steam drives the turbines turn the generators make the electricity. You're going to get really used to that phrase as we come on to one of our later physics topics. So as long as you remember, in a power station, water turns to steam drives the turbines turn the generators, and generators make the electricity. You've answered a chunk of a lot of power station questions there. What we do find is that the energy that's transferred to the surroundings via fission is much greater than the energy we would transfer in a combustion reaction. So this is why a lot of governments are looking at using nuclear power versus the fossil fuel power stations, because fossil fuel, so the coal, the oil, the natural gas, all of those rely on a combustion reaction. So when we burn them, we actually release a much lower amount of energy to the surroundings than we do through a fission reaction. So by using nuclear power stations, we can actually generate a lot more electricity using the same amount of fuel. So what I've given you here then is a little diagram showing fission reactions. What I want you to do is try to explain what that shows. Now, for those of you that have been watching those daily government briefings that we've had through this coronavirus pandemic, then that might look a little bit familiar to that diagram they've used of the R rate, so the transmission number. Because they've had a little look at, we start with that one person, and then if they infect 3 people, then this is what happens, and so on. And that picture that they used looked quite similar to this one here. And that's because it's showing a similar pattern. We start off with one fissionable substance, and as that nucleus is then split into 2, we release 3 neutrons. They're then going to join with 3 other nuclei. They will then split, and each of those releases 3 neutrons. So what we're actually doing here is we're generating something called a chain reaction. And hopefully you can see that starting with just the 1 neutron, the 1 became 3, those 3 became 9, those 9 would then become 27, and so on. So what we end up with is the ability to trigger more and more fission reactions, and they get bigger and bigger as time goes on. So what we actually do is we're releasing quite large quantities of energy quite quickly through a chain reaction. One thing we should bear in mind though is that a chain reaction can only occur if there are enough nuclei around that first one. So we need a decent mass of radioactive material. If we've only got a small mass of radioactive material, then the neutrons we've created would escape and the reaction would stop, because obviously there's not all of those nuclei there for those neutrons to collide with and so forth. If we've got a larger quantity of this radioactive material, then those neutrons are going to collide with the other nuclei and just keep increasing the size of that reaction. So inside our nuclear power plants, we've got this idea of a chain reaction occurring to an extent, but we control it. So here's a question: what would happen if the reaction inside a nuclear power plant was uncontrolled? Hopefully what we said is that the reaction keeps getting bigger until eventually we've generated so much energy, to all intents and purposes, we've done the same as a nuclear bomb. Now, that's obviously bad news, and we don't want that to happen in our nuclear power plants. And we've actually seen this happen before, going back to the 1980s in Ukraine, where the Chernobyl power plant actually had this scenario occur. The control of the reaction was lost, which led to it going into this meltdown. Now, you may have seen the mini-series of it, because obviously that happened way before you lot were born, but it's really worth looking into to find out a bit more about some of the risks of nuclear power. Obviously, not every nuclear power station undergoes some kind of uncontrolled reaction. And the reason for that is that within the nuclear power station, we've got these things called control rods. And basically, they're rods of a material that absorbs the neutrons. So when the reaction's getting a little bit too fast, we lower these rods down into the tanks, they absorb the additional neutrons and slow it right back down again. If we compare what happens in a nuclear power station to a nuclear bomb, then in a nuclear bomb we don't have control rods. We've got no method of slowing this reaction down. So once we're actually undergoing that detonation process, then it just keeps getting bigger and bigger until we release this huge amount of energy very, very quickly, because there's no absorption of those additional neutrons being created. So that's the first bit about nuclear fission. So really useful just to finish off by doing these couple of questions in your books. Once I've given you a couple of minutes to do this, then we're going to have a look at the second reaction, nuclear fusion. let's just double check those first part plenary answers then. So for question 1, if you wrote down either uranium or plutonium, give yourself a mark. And if you said the nucleus splits into smaller nuclei, 1 mark, and neutrons, a 3rd mark. So your first question is out of 3. Then for question 2, in a fission reaction neutrons are produced, 1 mark, and you need to absorb the neutrons to stop a chain reaction happening too fast, 2nd mark. So grand total of 5 for our plenary. Give yourself your totals in your book. So put a new little subheading for me of nuclear fusion this time. So the second process, nuclear fusion, is where we start with 2 small nuclei and they're going to join together to make a more stable nuclei. So they're going to join to make one larger nucleus. So write down our definition of what nuclear fusion actually is in your books. Now, what we can see is we've got 2 distinct processes. We've got nuclear fission, splitting, making them smaller, nuclear fusion, joining to make them bigger. Now, in terms of where we see nuclear fusion occurring, then again, this is something that's vital for our very existence, because this is what's happening in our sun. So that big ball of light in the sky, that is actually something that is undergoing this nuclear fusion reaction. And what we have in the sun are these hydrogen nuclei, and they're going to fuse together to form larger nuclei. So that means they'll either form different isotopes of hydrogen or they'll join to make helium. And eventually those helium nuclei are going to join together, and what we see is they just keep joining and fusing these nuclei together, and they're getting bigger and bigger and bigger until we make carbon, oxygen and iron. And hopefully you're sitting there thinking, well, hang on, our sun is just a star. If you look up at night, assuming you're not in the middle of a big city with tons of light pollution, then you can see huge numbers of stars in the sky. Each one of those is again this collection of gases that are undergoing nuclear fusion. So in all of those different stars that you can see, these smaller nuclei are fusing together to make larger and larger ones, and this is where things like carbon, oxygen and iron originate. They're actually in stars. So those elements that you're made from, they originally came from nuclear fusion in stars. As that's also happening, we're getting an energy transfer. So the energy is being transferred from a nuclear store by heating and electromagnetic radiation. And it's that electromagnetic radiation that travels through space from our sun to us here on Earth and allows us to have these lovely warm days that we get every once in a while. So thinking about what you know about the nucleus of an atom, see if you can come up with an idea about why joining two nuclei may be tricky. Hopefully we remembered that the nucleus is a positively charged entity. So if we've got two positive nuclei and we're trying to make them join together, that's going to be tricky because anything that's the same charge naturally repels. So because both nuclei are positive, they're actually going to repel each other and push each other away when they come close. So if we consider what happens in a fusion reaction, if we start off with two protons and we fuse them together, we form a substance called deuterium or hydrogen 2. Then what we can do is we can take that hydrogen 2 or the deuterium and we can fuse it to make tritium or hydrogen 3. So what we're doing here is we're slowly increasing the actual size of that nucleus because we're fusing smaller ones together. Then hydrogen 2 and hydrogen 3 can fuse, and that will form helium and a neutron. So what we see here is from starting off with just two protons, we then undergo these fusion reactions until we've made helium and a neutron. And what we can see in that little diagram at the bottom there, the reason that helium sits at the bottom of those dips is because it's the more stable form. So what we've done is we've taken less stable entities and created a more stable one. And as we've already said, this fusion just keeps making larger and larger atoms until we get to iron. The heaviest element we make by fusion is iron, but hopefully we know from our chemistry that iron's certainly not the heaviest atom that exists. The way that we can then make things that are heavier than iron is through a supernova. And a supernova, quite simply, is this massive explosion in space. And what we've got in the picture there, that's kind of like the remnants of a supernova, if you like. So this is this vast area of space that's then just glowing, basically, as a result of this explosion. And what we created at the point that that star went into its supernova were these heavier elements. So we said earlier on that one of the big problems with fusion is that the nuclei are both positively charged, so they naturally repel each other. So how do they join? And the answer as to why fusion can occur in things like our sun and other stars is because within that entity what we've got are really high temperatures and really high pressures. So the high temperature and the high pressures that we find within the star will actually allow fusion to occur. So thinking about your chemistry knowledge here, then see if you can suggest why those two conditions of high temperature and high pressure make fusion possible. Hopefully we remembered that if we've got high temperatures, then what we're actually doing is increasing the kinetic energy of the nuclei. Because anytime we've got higher temperatures, particles gain kinetic energy, therefore they're moving faster, and that means they're more likely to be colliding with each other. And in terms of our high pressure, hopefully we remember that that means the nuclei are going to be closer together, and therefore we can have fusion occurring. So the combination of the particles being closer together and moving much quicker means they will fuse. The last thing we're going to consider is about energy. Now, if we actually consider the mass, then the mass of the products of fusion is actually slightly less than the mass of the reactants. The reason that that's occurred is that the mass has actually produced a lot of energy in the form of radiation. So there's a formula that you may be familiar with, E equals delta mc squared. So E stands for energy, and energy is measured in joules. Delta M is the change in mass. So wherever you see that triangle, that's the delta sign, and it just means change. And then M is our mass. C is the speed of light, and it's squared. So what we hopefully know is the speed of light is 300 million meters per second, so pretty quick. And therefore, even with these tiny changes in mass, because we're obviously timesing it by the speed of light squared, this is going to lead to huge amounts of energy being given out. So tiny changes in mass, result in huge amounts of energy. Hence why our stars are so bright that we can see them from here on Earth, many millions upon millions of miles away from them. So the final thing for today and the final thing for P6 is the plenary questions. So those who have the target grade up to grade 5, column on the left. Target grade over a grade 5, it's the column on the right. So I'll leave this up for a couple of minutes today, but as always, if you need longer, hit pause and take as long as you need. It is worth mentioning now that this would also be the end of our term. So for those of you obviously in my classes, this is it. We are done with our learning for this year, and we'll be back in September, hopefully in school. For those of you from other schools that have been joining us on this little internet school journey, then I hope you found it useful, and I wish you all the best in your return to school as well.